workshops or seminars. This one's by the Working Group on Structures and Systems Health Management. And our first speaker today will be Lauren Katch. Lauren is a PhD student working with Dr. Arguelles, and she's nearing completion. And her background is she was undergraduate and double majored in mechanical engineering and engineering science, and then went into the ESM graduate program. So she's going to talk about, I will read her title for us, Line Defect Inspection of Silicon Using High Frequency Shear Ultrasound. There's some interesting keywords there.
Thank you, Dr. Ilseman, for the introduction. So I'm Lauren Katch. I work with Dr. Arguelles, and the work I'm presenting today will be in collaboration with the Imperial College of London with Wei Yo and Dr. Bo Lan. And so we'll be talking about defect detection in silicon wafers. So to start, we can think about where are silicon wafers, right? Silicon wafers are really industrially relevant. They're in photovoltaic solar panels. They're in the electronics that we see in all of our devices. And so silicon is quite a prevalent material in the industry. And specifically within the semiconductor industry, which is quite large, evaluated at $527 billion, I'm sure growing past the statistic, right? Quality control is really important. And currently there's quite a loss of income of over $78 billion because of silicon wafers that are currently not passing quality control checks. And so quality control within the silicon industry is both important and also an expensive problem to address. If we look to certain defects that are showing up within the silicon industry, there's one specific type of defect that is currently going undetected and is posing challenges for this quality control, and that's back surface crack. So if we consider, I'm going to use the laser pointer to point so that everyone online can also see. But if we consider these back surface defects that on the back surface from cracking during the manufacturing process, these are long and narrow in terms of how they propagate from the back surface, and they're currently being detected with what's called conventional normal incidence ultrasound, and they're not showing up. So we can see in this image on the right, in the attempts to detect these defects, there's no indication. So this gray square of scanning doesn't have any indication of the defects that are in the center of this wafer or at the bottom edge of this wafer. And so we need to work on modifying these techniques to be able to detect these defects. And so we proposed a modified setup, right? So currently there's this normal incidence setup where you have your ultrasonic transducer probe that's oriented normal, and you have your silicon wafer placed in an immersion ultrasonic tank. So you use water as a couplant, the waves propagate through the water and then into your silicon sample, where then they're able to interact with your defects and you're able to look at that reflection and scattering, right? So if we're at normal incidence, we have this sensitivity to this very narrow dimension. And so that's why they're currently not being very well detected. If we switch to this oblique incidence setup like the one on the right, now we're able to have our waves propagate at an angle, and we're able to have this sensitivity now to this larger height dimension. So we're anticipating that if we move to an oblique incidence setup, we'll be able to drive up our inspection resolution and sensitivity. And we're also able to take advantage of shear waves, which have lower wavelengths than longitudinal waves, which are used at normal incidence. So also by looking at a shear wave modality with a lower wavelength, we'll be also able to increase our inspection resolution. Now, one of the challenges associated with moving to oblique incidence from a normal incidence setup for silicon is the fact that silicon is an anisotropic material. So this means that the material properties vary depending on the direction that you look at within your silicon wafer. And silicon specifically is a cubically anisotropic material. So there are planes of symmetry in terms of when we're looking at the behavior where the material properties are uniform. And so if we use the conventional normal incidence setup, we propagate along one of these symmetry planes, along this E3 axis. And so when you do normal incidence, the anisotropy isn't a barrier. But now when we switch to oblique incidence, we're not necessarily propagating along a symmetry plane, so the material properties are going to be non-uniform depending on the directions that we're looking at. And this is going to have a direct relationship to our wave propagation, right? Because the material properties and the wave propagation go hand in hand. And this shows up within our ultrasonic immersion setup. So if we're considering a constant propagating from our fluid that's at an angle of theta 1, and it's a longitudinal wave in our fluid, depending on the inspection direction that we're coming in within our silicon, say if we're coming in along the x-axis or if we're bisecting these x and y-axes, now the material properties in our sample will be different. And this means that our resulting wave propagation behavior within the solid for a given propagation coming from the fluid are going to vary. So we're going to have non-uniform wave refraction. So this angle theta 2 is going to change, and also our wave speed is going to change. So the speed of our wave and our wavelength, right, since that's related to our wave speed, are going to also be directionally varying. The third challenge associated with moving to oblique incidence with the anisotropy of silicon is wave focusing. And so we really like to use focus transducers for these inspection techniques because we're able to have this conical surface that excites the wave. We send in the conical wave beam, and then it refracts at the fluid-solid interface and forms this really ideal circular focus within our solid. So we're able to decrease our spot size and increase our resolution that way, and also have this energy be well concentrated within our sample. And this refraction is governed by Snell's law. So if we consider one of our rays coming from our transducer, if it's coming in at theta 1, it's refracting at theta 2 and propagating at a wave speed of v2. But as I was saying before, right, we have this material property directionality in our anisotropic silicon, so the refraction is not necessarily going to be uniform. And in fact, actually, the angle that we're propagating within our silicon is going to change the velocity that we're propagating in the silicon. So if the wave is propagating at, say, 30 degrees versus 40 degrees, the wave speed is going to be different in our solid. So if we're going to move to this ultrasonic oblique incidence setup and we're looking at what the wave focusing looks like, now we have these non-uniform refractions because of the varying velocity in the solid. And so our focusing behavior, we're not really sure what it's going to look like, right? These rays can be refracting non-uniformly. So we're not sure, are they going to produce a focus? What is that focus going to look like? And what are the ramifications for inspectability? Okay, so that brings us to the main question of this study, which is really how does this anisotropic wave propagation in combination with the focusing affect our defect detection and wave scattering? So to do this work, we worked with Intel, and they were able to provide us with these silicon wafers that have these laser engraved trenches on the back surface, which are going to act as pseudo cracks. And we placed our defects at different orientations relative to our crystal axes because we wanted to understand the effect of anisotropy. So like I said before, there's this symmetry axis in the silicon. So here we can see one of the crystal symmetry axes is aligned with the 0-degree defect. And then we placed some defects that are offset from the symmetry axes in both the positive and negative orientations. And so we would anticipate that if anisotropy is going to be a driving factor in our response, not only are we going to see varying behavior, but the behavior should be symmetrical across the 0 degrees, in that both of these 15-degree defects should be showing the same behavior, and the 45 and 45 degrees defects should be showing the same behavior because they're located at opposite ends of the symmetry plane. And these defects, again, are placed from a back surface perspective. So when we're inspecting, they're not on the top surface, they're on the back surface in a long dimension. Okay, so then we go and we try to inspect these defects. So we place them in our ultrasonic immersion tank. So they're shown here. You can see this is our silicon wafer. It's placed on the standoff in our water tank, and it's placed on top of a rotating stage. So what we did is we scanned our defects with both a 100 megahertz focused and unfocused transducer, and this was to uncouple the relationship of what is happening with focusing versus unfocusing in the presence of the anisotropy. And then we scanned each of our defects individually so that now we're able to bring in that defect directionality component. So we started off with this 0-degree defect, and we placed our defect such that it was perpendicular to our transducer. And then we raster scan over the defect. So we just do an area scan over the defect. We then move on to our next defect, so say the 15-degree defect, and we use our rotating stage to then rotate our sample again, such that now our defect is at the same orientation, right? So our defect is now, again, perpendicular to our transducer. We area scan over that, We then want to go and inspect the 45-degree defect. So we rotate our entire sample such that our 45-degree defect is now perpendicular to our transducer. So we do all these rotations and scans individually such that the geometry of the defect with respect to the transducer is identical across all our scans. And the only thing that's varying is how these crystallographic axes are oriented relative to the defect. So we'll be able to understand how the anisotropy is changing our ability to detect these defects. So on this next slide, this is what we get from a single signal from one location on our sample. And we can see the comparison of the unfocused versus focused transducer case. And so we can see on the left, we have the scans from our unfocused transducer, and we can see that with respect to a reference location, we don't get any sort of strong signal coming from the defect when we know that we're aligned for that reflection to be coming. So we're not able to use unfocused transducers to have the sensitivity to the defect. Rather, when we switch to the focused case, we can see this red sinusoid is present in the presence of the defect. And so this is our reflection and our scattering that we're getting off of the defect. So we'll be moving forward with the results that are looking exclusively at the results from the focusing. And this really drives home the importance of understanding the focusing behavior because focused transducers are required to detect defects for these cases. So we then take each of these individual signals and we map them across our areas. So these images are called C-scans, and they're going to be our area scans where we're time gating the reflection and plotting the maximum amplitude that we get within that time gate for a given location of our scan. And so we can see here again that our defects are oriented the same for all of these configurations, so that our defects are vertical for all these different configurations. The variation that we're seeing is a result of the material orientation. So these crystal axes are rotated at different orientations for these scans. I want to first bring your attention to what we're seeing here, the differences of our maximum amplitude. And we can see that we have quite a variation in terms of the maximum amplitudes that we're seeing. Our 0-degree defect is giving us an amplitude of 0.9 volts versus when we're looking at defects of other orientations, now our amplitudes are decreasing. So we can see that the anisotropy is driving a difference in terms of the amplitude that we're seeing. And this has ramifications for inspectability because these defects are all the same size, but depending on how it's oriented within your silicon is going to affect the amplitude that you get back. We can also confirm that we see some of the symmetry in the behavior, right? So it's maximum at 0, it drops to around 875 and 828 for the 15, and then it drops to our lowest case for the negative and positive 45-degree cases. So we can confirm that the anisotropy is, again, right, one of the factors that's affecting this because we have that symmetry we were anticipating. It's more interesting, right, if we start to look at these shapes that we're seeing, and we can see that for our 0 and 15-degree cases, we have what we'll call a one-lobe scattering pattern. But what's really surprising is if we go to these negative 45 and 45-degree cases, where we have this two-lobe scattering pattern. Because in the center here, our transducer is placed and oriented so that it should be reflecting off the center of our defect. And it's surprising that we don't get a very strong amplitude at that point, and rather we get this splitting of the scattering that we're seeing from the defect. And so this is something that we wanted to dive more into to try to understand the fundamentals of the wave propagation and the wave focusing and how this is affecting the overall behavior that we're seeing here. Okay. So moving forward, I'll be diving in specifically to the 0 and 45-degree cases, where our 0-degree case is again aligned with one of our symmetry axes directions, and our 45-degree case is bisecting our symmetry axis. And so we'll go more into understanding, right, the fundamental wave propagation and this focusing behavior. And we do this first through ray tracing. So ray tracing, I sort of alluded to it previously, right, but we're able to draw these ray vectors that come from our conical surface, that is our transducer, and then map how they refract through the fluid-solid interface. And the refraction, again, right, is going to have this interdependent relationship of the angle of refraction with the wave speed we see in the solid. So we use Snell's law in combination with Christophel's equation to understand the variations we're seeing in the refraction and in the wave speed. We do this plotting, and then we're able to map what our focusing behavior looks like on the back surface of our silicon wafer. And so this is zoomed in on where all those rays are concentrated on our back surface, And we're able to see that for this 0-degree case, we have a relatively not interesting focusing behavior, right? It looks pretty single in terms of the shape we're seeing. It's pretty elliptical in terms of the focusing behavior we're seeing. And so this aligns with the scattering behavior we're seeing, right? So the 0-degree case, the scattering was one lobe, the focusing looks rather elliptical. So these behaviors are aligning together with what we're seeing. We then worked with Imperial College to get these great simulations from POGO, where we're bringing in the frequency dependence. So ray tracing doesn't have frequency involved, but they were able to do these simulations for us to dynamically simulate what happens during the wave propagation. And you can see that it's pretty dynamic in terms of how the wave is forming within the propagation, but that overall, I'll try to get it to simulate again, right? We can see that it is forming a relatively uniform focus once we're reaching the back surface. And we can see this actual direct mapping right here on the right, where we're again confirming that for this 0-degree orientation, we have a relatively elliptical focus on the back surface. It's more interesting, right, if we go to the 45-degree case where we are seeing the surprising 2-lobe scattering pattern, and we go to a ray tracing and we look at the focusing on the back surface, and now we see what we're going to call a butterfly-shaped focal profile, right? So there's these sort of lobes occurring to it. There's some variations we're seeing. And so again, we're consulting some of the POGO simulations to bring in that frequency dependence. And we can see that here, we're now having this wave splitting. So our wave focus is actually splitting into this split focal profile. And this is, again, shown more clearly in this static image. So you can see dynamically how this splitting is occurring. But in our static image, we can see that our wave focus is really split in the solid. And so this is going to correspond directly to that scattering behavior we were seeing, where we have this split focus, and now we have this 2-lobe scattering pattern occurring for this defect. We took it one step further with our finite element simulations and modeled the full scattering that we're seeing from the defects. And again, we can see good correlation in terms of what we're seeing from the simulations and what we are seeing experimentally, where for our 0-degree case, where we're aligned with that symmetry axis, we get 1-lobe scattering at a higher amplitude. Compared to the 45-degree case, we get 2-lobe scattering, and that's a lower amplitude. We then wanted to go back and look at the effects of focusing, again, with the finite element. So we weren't able to detect it from the experiment, but hypothetically, what would the scattering look like for the unfocused transducers? And so we can see here on the left portion what our beam modeling looks like for the unfocused transducers. And we can see that the behavior becomes pretty not interesting for the unfocused transducers, right? You get the circular shape on the back surface. And so there's still some of those amplitude variations that persist, where for our 0-degree case, we have a higher amplitude than the 45-degree case, but now the shape is pretty uniform for both of them. Again, in the scattering response, we're getting pretty elliptical scattering behavior from both cases. And for the 0-degree case now, again, we still have a larger amplitude. So we can see that the amplitude variations are really driven by the anisotropy because they're present in both the focused and unfocused cases, and that the overall scattering shapes were really primarily driven by the focusing. I also want to bring your attention to the overall difference in amplitude that we're seeing with the unfocused transducers. And even from a finite element perspective, these are 2 orders of magnitude smaller than what we're seeing with the focused transducers, which really just drives home the point that focused transducers are needed to have the sensitivity and the concentration of energy required to get a signal from these defects. And so using unfocused transducers alone won't have sensitivity to these defects. And this brings us right to our 2 main conclusions, where we have this anisotropy that's driving these amplitude differences that we're seeing for defects of different orientations. When we're along the symmetry axes, we get higher amplitudes for both focused and unfocused cases. When we're offset from those, now the amplitudes start to drop. We also saw the impacts of focusing and our focused transducers really driving this directionally dependent focal profiles, where we saw that elliptical and butterfly wing focal profiles, which in turn are going to directly cause these differences we're seeing in the scattering pattern, where we are getting the single lobe and double lobe scattering pattern. And so with that, I would like to end my presentation and thank again our collaborators, Imperial College and Dr. Arguelles, for her guidance, as well as the various funding agencies for this work, Intel, and then the ASSP Fellowship. Our work has also been published rather recently in November on this work in IEEE. So at this point, I'm happy to answer any questions. Thank you.
Questions from the audience?
Here I give the audience a chance.
I've got a lot of them. The silicon is on the water, is in water.
Silicon is in water for these, yeah. So everything is shown in an ultrasonic immersion tank setup.
And I missed the beginning of the talk, so what's the application?
Yeah, so this work was funded by Intel, so it's directly impacting when we're thinking about silicon wafers being used in the electronics industry or in the photovoltaics industry. Quality control is really important in terms of the end resulting quality of your defects or of your dies. And so being able to detect defects early on is really critical. So the defects that we're looking at for this study of these back surface cracks, these are currently going undetected. So we wanted to show the sensitivity to that, but then also look at all the other considerations that come with detecting these defects.
Is that like one of the most common defects, like the vertical?
They were saying that it was common, so Intel wouldn't specifically dive into sort of how these are showing up or more of the specifics, but they specifically hand selected this defect geometry. So we can kind of infer from that the importance of understanding these.
I was wondering if you can put the transducer on the side instead of on the top, then you'll be able to, then you have a propagation that is perpendicular to the direction of the defect.
Yes. So that was something that we had thought about doing. The challenge is that these wafers are really thin.
Oh, yeah.
So they're 775 microns thick. And so getting the propagation to be really clean in that direction is going to be pretty challenging.
So if it's underwater and the transducer is not in contact, how do you deal with that reflection? Do you have a high impedance to water?
Yes, so we use the water because it's able to act as a pretty ideal couplant compared to a couplant gel or something like that. We're able to get also good transmission from the fluid into the solid, but you're right, there is definitely some energy loss inherently from that, especially when we're looking at the high frequencies that we're looking at here. So we're using 100 megahertz for these, which is definitely on the kind of upper end of what you see conventionally for immersion ultrasound. You have a question? Yeah.
Yeah, I'm curious about your defects. They're pretty small. Did you make those here, or did Intel make them?
So they made them, yeah. So they made them with a laser, and then we confirmed the cross sections by cutting them and then imaging it through that process. So they used a laser to make them on their end. We looked a little bit into trying to make some on our end, but we haven't explored that fully at Penn State.
I'll ask one. When you were talking about your initial testing, you were coming at the defect from a lot of different angles. Do you think that'll be necessary if this were to be used in the end for inspection?
That's a great question. That's something that Intel was really interested in because we are trying to optimize our sensitivity for all these defects by kind of keeping the corner trapping as ideal as possible. But what we did do, and that's kind of in the name of the blind defect inspection, is we did have a sample ultimately that had defects in it that were positioned at a bunch of different orientations, and we were able to show sensitivity to the defects at different orientations. So the rotations were not necessary from a pure sensitivity perspective. There were then kind of skewed scattering profiles, and things quickly got a little bit more complicated from that perspective. So we're explaining all of it with the background wave propagation became a little bit more challenging, but we're able to show sensitivity to the defects of the different orientations.
So a bigger picture question would be, when they inspect their wafers, do they do 100%? Do they inspect 100% of the wafers, or is it a statistical? We inspect 10% or something. Like that?
I'm not exactly sure how they're currently doing it. So they are using the ultrasonic immersion setup, right? So they're currently using normal incidence ultrasound, and then they were going through and looking now at the shear oblique incidence ultrasound because of the work that we've done. And so I would guess that they are probably doing some batch down selecting and not putting all of them through an immersion ultrasonic setup. I think that would just be very time consuming, but I'm not exactly sure.
Our Dr. Horn in ESM used to give a talk to the undergraduate seniors about the economy of scale in semiconductor manufacturing. The numbers are astounding, and I think that really drives the importance of the CHIPS Act. We get some manufacturing in the U.S.
Definitely.
I wouldn't have time to do this.
Okay. I don't know. Is there a way to check online, or we would have heard online?
I have a question. Can you hear me?
Hello. Yes.
Oh, sounds like that.
Hi, Lois.
Hi. Great presentation, Lauren. I have a question regarding the inspection. So you are using the angle beam inspection, right? So you're oriented at an angle. So whenever the wave hits the defect, it would result in a lot of mode conversions, I believe. So whenever you take a complete scan, I believe you will get a lot of artifacts because of the mode conversion from shear to longitudinal wave and all. So I was wondering, how do you account for those artifacts in your final scattering image that comes from the mode conversions?
Thanks, Lois. That's a great question. And that's something we were definitely considering when we were thinking about our setup. And so when we were positioning our ultrasonic transducer, we placed it at 12.5 degrees, which there's no singular critical angle because of all the different wave speeds we see in the solid, but that placed us at pretty much around a close ballpark average of the critical angle. So we were really expecting that shear waves were going to be the driving factor in our solid, propagating at around 45 degrees. And then that the longitudinal waves, a lot of them, right, we would be past the critical angle, so a lot of the longitudinal waves wouldn't be interacting with our defects, and that if any of the longitudinal waves were going in, they would be going at quite a bit larger angles than what we were seeing. There is inherently, because we have the conical surface, right, there are some waves that propagate at different angles, but we're able to kind of isolate a lot of the shear components because of the time of arrival that we're looking at. And so we calculated the expected time of arrival in our A-scan image. That's all the way back here. So the time gating that we were doing was also based specifically for the shear wave. We looked around a little bit to try to see if there were other more clear reflections that were coming from a longitudinal type mode conversion, but there wasn't necessarily a clear reflection coming from those. So there might be some additional interactions, but they definitely weren't in the magnitude of what we're seeing from the shear. Does that answer your question?
Yeah. Thank you so much.
All right. Well, in the interest of time, Lauren, thank you very much for the
Thank you so
presentation. God, for slight amounts of anisotropy that makes for such a mess. It's a great topic for PhD study. Words longer now. Okay. Our second presentation today will be by Keirn, who is a graduate student in engineering science mechanics, and he is finishing up his master's thesis, pretty much done. But he went through the engineering science undergraduate program as well, and was part of the integrated undergraduate graduate program. So that's how he's finishing up his master's degree now. And his topic today is thesis topic, determining the bounds of the frequency stop-bandgap in elastodynamic metasurfaces for the S0 Lamb wave excitation.
Thank you, Dr. Wilson, for the introduction. As he mentioned, today I'll be talking to you about my master's thesis work as part of the NSF Metasurfaces project. So to begin, I want to just briefly define what exactly is a metasurface. And essentially what a metasurface is the 2D version of a metamaterial, which is a engineered structure such that through a combination of its material properties and geometric properties, often exhibits unique properties that can have a variety of uses. In the field of acoustics, the primary uses for them often involve some degree of wave steering or wave attenuation and vibration control. And so essentially, these can be used for things ranging from vibration isolation in any application where you might not want vibrations, for example, or if scaled properly, to potentially be used to mitigate earthquakes and protect buildings from earthquake vibration. For many previous studies, they often focus on individual modes, and so in my specific study, I'll be focusing on the S0 land wave mode in plate. Previous studies often involve the design of these metasurfaces using local resonances. So there are a couple different modes in which these metasurfaces can operate or work through. Specifically, we'll be looking at the effects of local resonances. And these processes often involve designing resonators that work for a single frequency. So you create the resonator such that it works at whatever specific frequency you design it for. However, this often involves then creating multiple resonators at different frequencies in order to create a grading effect in the final metasurface array. And so this is potentially limiting in that you are limiting the resonator geometries that you have to being something that is easily tunable for different frequencies. And it is potentially beneficial to instead create resonators that on their own just have a naturally wider band gap. And so the idea is that if we can come up with a alternative methodology for designing these resonators, then we only need one resonator design instead of multiple for different frequencies. And so this is where potentially topology optimization can come in, where we can then use that to create less intuitive designs for these metasurfaces, such that the resonator itself has a naturally wider band gap. However, in order to motivate this optimization process, we first need a parameter in order to efficiently determine whether or not the optimization is doing well or not. And so this is where the primary purpose of this study comes in. Recent studies have already shown that for 3D bulk materials, metamaterials, there seems to be a connection between the band gap of the metasurface and resonances and anti-resonances of the resonators that create the metasurface. And so this study attempts to show that there's a similar connection also for the case of plate waves. And so showing that the resonances, as shown on the figure here, and the anti-resonances are connected in some way to the band gap that we see based on a lower transmission ratio, usually defining it by a certain value. In most cases, for my purposes, I usually define it as transmission ratio below 0.4. And so in this presentation, I'll be talking mostly about my numerical results that I got using COMSOL and then post-processed in MATLAB, starting with the results from frequency response analysis, and then going to dispersion analysis, which is something that's often done in previous studies to look at the band gaps for these metasurfaces, and then talking about the full metasurface model where I'm looking at the transmission. So to start out, I want to talk a little bit about the frequency response function. In order to create the excitation for said response, I first need to look at the type of particle motion that we see as part of the S0 land wave mode. And so as we can see in the plot here, the S0 land wave mode is primarily longitudinal in nature. And so that means that the particle motion is in the same direction, or at least primarily in the same direction as the wave is propagating. And so when we apply resonators to the top of the plate, we can see the contact area where the plate is in contact with the resonators, that the particle motion at the bottom of the resonators is in the X direction. And so using that, we can create or we can say that we can use a horizontal harmonic excitation at the base of the resonators in order to approximate what the wave motion would be like acting on the resonators in order to get the frequency response. And so we can see here how the response is for the three different components. So U being X direction, V Y direction, and then Z or W in the Z direction. Using the same idea, we're taking the surface average displacement at the base of the resonator in order to get these plots. Using this same idea, we can say that in order to get the desirable clamping effect that we like for the local resonances creating the metasurface, we should be looking at the X component, so the U component specifically, such that whenever we hit the anti-resonances, the resonator is essentially not vibrating or is not moving at the base at its base where it's in contact with the plate, and so it's clamping on the plate, preventing vibrations at those frequencies. Moving on to talking about dispersion analysis. The primary purpose for the dispersion analysis is to confirm and identify the possible band gaps that we see in the metasurface, because these dispersion curves often show all the possible band gaps that we would potentially see, whereas the frequency response is mostly an approximation. And so doing this, we can see using the mode shapes at each of these points as indicated on the plot. We can see A and B here are two longitudinal modes of the prismatic resonator in this case, and C, D, and E, F are all flexural resonances. Knowing that the particle motion for S0 Lamb wave propagation is primarily in plane, so in the X direction, we would say that the flexural modes are what would be applying the what would be related to the S0 Lamb wave mode. Whereas for the opposite mode, which would be A0, particle motion is primarily out of plane. So if you think of a plate as kind of bending, the particle motion out of plane, so the longitudinal modes would be what we're primarily looking at. So the yellow highlighted region here indicates the band gap that we would expect being bounded by longitudinal modes for the A0 Lamb wave mode. And then the orange highlighted regions are the two band gaps that we expect in this frequency range for the S0 Lamb wave mode. And so now, looking at the metasurface model, the plate was designed such that it is iterative depending on the frequency and wave number. This was because the plate overall is rather large in order to ensure that for our frequency range, we have enough wavelength in order to properly model each wave, essentially. And the plate needs to be iterative in size so that the total element count remains relatively low, so that it's easily computed. And so a frequency range was determined around 100 frequencies, ranging from 20 kilohertz to 150 kilohertz. And the model was created such that in the Y direction, the width is constant. The height is always 1 millimeter, so we have a 1 millimeter thick plate. And in the direction of wave propagation, the length is iterative depending on the wavelength of the S0 mode that we're exciting at each frequency. And we can see here that the loading region, and then we have a small incident region, and then the resonator region where we'll be placing the resonators, and then transmitted region where we'll be exporting displacements in order to use for further processing. The entire plate is surrounded by a perfectly matched layer region in order to prevent reflections from the ends and from the sides. So we're only looking at the initial wave interaction. And so from there, using the exported displacement from the transmitted region, we take a fast Fourier transform over those displacements over the length of the transmitted region in order to get the wave number spectra for each individual frequency. And then at each frequency, we're taking the peaks. So this wave number is associated with the S0 land wave mode. We're taking the peaks and taking the ratio of those two in order to get the transmission. These two plots come from both the baseline and metasurface case. So baseline being the case where there are no resonators on the plate, and the metasurface case being where we're adding the resonators. And so doing this with our prismatic resonators, which we created to have geometry such that the anti-resonance, or at least one of them, was located between 40 and 60 kilohertz. The exact number wasn't overly important. But we wanted something in this range. And so the anti-resonance being at 41.5 kilohertz, as shown in the frequency response before, results in this band gap and then the upper band gap shown here. We considered two different arrangements for the prismatic resonator, one being closely packed together in an inline scenario, as indicated by the 10 by 3 case, so 10 resonators by 3 resonators. And then in the other scenario, it's considered a more spaced out arrangement, and it's off-centered, and it is staggered. So it's 4 resonators by 4 resonators, and it's off-centered, staggered. So that's the naming convention. And we can see the result that we have here. We can see that we have clearly a band gap associated with the 41.5 kilohertz anti-resonance, and we have another band gap at the upper frequency. Additionally, an experiment was also created in order to verify these results, showing here the experimental setup and using a plate with said geometry. The process was overall essentially the same as the simulation, where we're taking displacement measurements along the transmitted region for both a metasurface case with resonators and a case without resonators. And then we're taking the ratio of the S0 lamb wave mode portion of the wave number spectrum in order to get the final transmission plot. And so that is shown here, where we're plotting the waterfall plot of all signals over the transmitted region. So each portion here is a different signal measured at a different point. And we're taking the 2D FFT in this case, and then we're taking the maximum values along the peak, along the S0 lamb wave mode, and we're getting the transmission from that. Or then we're taking the ratio of the two, and we're getting the transmission. And so from that, combining that with the numerical simulations and the dispersion analysis, we can see that all three have pretty good agreement of where the band gaps are for the prismatic resonators. The highlighted region is the band gap as indicated by the dispersion analysis, and then the dark blue is the numerical simulation of the full metasurface, and the lighter dashed lines are the two experiment cases. Experiments were taking at 2 different frequencies simply because of the bandwidth of the excitation we were using. So we wanted to use 2 in order to get both band gaps. And so from this, we can then add in overlay of the frequency response function. And we can see that the anti-resonances both appear within the band gap region that we see. And the anti-resonance appears to indicate the upper bound of the band gap in this case. So using this idea, we can say that the anti-resonances would be defining where the band gap is, and then the resonances create bounds of how wide the band gap can be. So using this idea, we can say if we push the resonances away from the anti-resonance, so if we push the 2 resonances away from the anti-resonance, then this band gap could potentially increase as a result of doing that. And so this is the parameter that we're looking at to motivate the topology optimization process. And so doing that, I want to really quick thank Daniel Guzman for his work on developing the finer details of this process. But doing this, we can create an objective function such that the blue term here is used to target a specific anti-resonance frequency. So create the resonator such that the anti-resonance lines up with the minimum point of this plot here. So in this case, we're targeting 50 kilohertz. And then the green term is used to push the resonances away from that anti-resonance. And so if we're targeting 50 kilohertz, we want the resonances of whatever resonator we design to be pushed away from the 50 kilohertz. And doing so, we result in this geometry, as I showed previously as well, that we very affectionately called the lemon because of its shape. And so using this geometry, there was a restriction on the base size such that it was roughly similar to the same base size as the prismatic resonator, so that we're covering approximately the same surface area on the plate. And this is also the geometry that motivated the 4x4 off-centered staggered case that I showed previously. That case is the scenario where the resonators are packed together as closely as possible for the lemon resonator, because it is overall a little bit bigger than the prismatic. And so doing so, we considered of course, the same geometry as before, as well as another inline case, simply to confirm the results that we were seeing, and that it wasn't, dependent on whether it was inline or staggered. And we can see here that we do have a noticeable band gap around 50 kilohertz as a result. And overlaying the frequency response, we can see that the anti-resonance located at about 50 kilohertz, and the resonance is all pushed away pretty far away from where that anti-resonance is. It is worth noting that the resonance does not determine the exact upper bound of the band gap anymore. The exact reason for this is not entirely known, although the idea is that potentially the spacing between the resonators in this scenario is approximately the same. It just so happened that it happened to be the same, roughly the same distance as the wavelength of the A0 mode around this frequency range. And so the thought is that because of that, we already know that there is some mode conversion that often happens. And so because of that, the band gap is not as wide as we originally expected it to be. However, it is still wider than the baseline or the prismatic case that we showed earlier. And we can see those results here, where clearly the band gaps, as they're associated here, at least below the frequency range where the width, the resonator spacing starts to have some effects. The band gap of the prismatic resonator compared to the lemon resonator is clearly that the lemon resonator is an improvement, so wider frequency range. And in the case where the two resonators have the same geometry or same array geometry, as well as approximately the same base surface area, so everything is about as similar as possible, the lemon resonator is even better in that case. And I've shown in my undergraduate work that the number of resonators can have an effect as well. Typically, more resonators increases the band gap. And so the 10x3 case having a larger band gap is as expected, because there are just more resonators in the array, at least in the direction of wave propagation, for the resonators to clamp down on the plate, so it's more effective. And so I've shown in this presentation that there is indeed a connection between the frequency response and the band gap of the metasurface. And using this to motivate the topology optimization, we can use this to create non-intuitive resonator designs with wider band gaps. And so showing that through the connection of the frequency response, as well as confirming it through the dispersion analysis, can show the connection between all three. And we can get results in less simple geometries, more complex geometries as a result. And so that's the end of my presentation. Thank you.
Questions from the audience?
in person or afar?
Yeah, good.
Is there a specific reason for the number of nodes or number of methods you take in propagation direction?
Yeah, so primarily, as long as it's, we wanted to look at more than one row, simply because one row isn't very effective. And as I mentioned before, the number of resonators does have a minor effect on increasing the band gap. However, the number of resonators does not increase the band gap beyond a certain point. So simply adding more rows is not going to infinitely expand the band gap. It will only go to up to a point. And so that was kind of used to determine that more than 3 rows wasn't really going to change anything very much. So as long as that condition was met, that was kind of how we motivated that.
Is where, this is kind of conjunction with that question. This is where metasurface on a plate is much different than metasurface on a half space. In the case of seismic, where you're trying to control wave propagation in the earth, you have essentially a half space. And there, the number of resonators along in the direction of propagation has a much bigger effect, because the shorter the area where shorter the length of the area where the resonators are, the more tendency the waves that get skewed downward will come back up. We'll just go down and come back up to the surface on the other side.
Yeah, thanks, Jeremy. So how do you think that this would translate to other wave modes? So you looked at the S0, right?
Yeah.
So how repeatable would it be, or do you think it'd be more challenging to look at the other types?
Yeah, so previous studies have already used the A0 mode. One example being the very first thing that I showed I didn't mention it before, but so this study here uses dispersion curves and primarily focuses on the A0 mode and does a very similar process. And so it is, at least within plates, a kind of, I don't know what the word I want to use is, but a transferable process between modes. So you can use this for the S0 mode. Based on the dispersion analysis, we would say that, or I would say that the band gap for the A0 mode would be something correlated to this, or something connected to this more. And so you would do basically the same thing, except you would probably use a vertical excitation then to model the out-of-plane displacement, which is what's primary in the A0 mode, and other associated changes along those lines. So yeah, I did look at the A0 mode a little bit. It just so happened that the band gap for that was actually kind of too wide. You couldn't really see it very well, especially with the A0 mode being a lot slower in wave speed. Looking at that in the experiment, we would have needed a much larger range. So it has a smaller wavelength. And so in order to look at it, it would have been just a little bit more challenging. So that's why we did the S0 mode.
Thank you.
Well, not seeing any other hands fly up for more questions, I think probably a good time to end. So thank you, Jeremy. Are there any more seminars this semester?
I don't think there's any more this semester, but there's one second week of January. We've got one early next. Okay, look forward to that.
Start again in the spring. Thank you very much.
Yeah. All right, no questions. Is that a good thing or a bad thing? Depends.
Great presentation.
Thank you.
As always. I was not saying that because you know.
I appreciate it.
It's expected.
Yeah.
This is finally the end of just work. I feel like
Yeah.
I feel like part two.